Welcome to the first presentation by Nikkiso at the World Hydrogen Summit. We'll be presenting again later at the full summit stage. I'm Jeff Odell. I'm a senior process engineer at Nikkiso, and I've developed the hydrogen liquefier for our company. So, who is Nikkiso? Nikkiso is an independent supplier of cryogenic products upstream and downstream in the value chain, from pumps to vaporizers to liquefiers, as well as turnkey solutions. In this presentation, I'm going to walk you through a lot of the decisions that you'll end up facing when designing your entire liquid hydrogen system. We're going to look upstream to the generation side, where you're going to be presented with challenges such as, what pressure do I generate at? How much do I need to purify my gases? Then we're going to move into the liquefier section. We're going to talk about turndown, as well as how ambient temperature affects your entire system. Then we're going to look downstream and see how boil-off gas can be managed, as well as how you operate your storage tank. So, the first handshake is supply pressure. And the balsa liquefier, Nikkiso's liquefier, has been designed to take feed pressure of hydrogen from 250 to 350 psi. This keeps you nicely supercritical, which is very good for your overall plant efficiency, while not requiring excessive feed gas compression. This results in a lower total system power cost. Now, different sources of hydrogen generation will end up producing at different pressures, but you'll see that even if you have atmospheric hydrogen generation, it still pays to compress up to these pressures. Additionally, operating at these pressures gives you a zone of stability, essentially, where small deviations in your feed gas pressure are dampened out by the liquefier and don't cause major process upsets. So now let's move on to contamination. There's a wide variety of molecules that can come entrained in your hydrogen feed supply. Unfortunately, hydrogen's so cold that almost every atom in the universe will freeze at liquid hydrogen conditions. Now, rather than going into the depths of all of these different molecules, we can just simply group them into two categories: the high temperature freezers and the cryogenic freezers. And when you're speccing out your pretreatment system, just focus on the high temperature freezing components. We can deal with the cryogenic freezers internally, but we need you to make sure that you remove the water and CO2. Ultimately, PSA vendors love to tell you how many nines of removal that they can offer, but just focus on the high temperature freezers. The bulk removal isn't as important. So, if you're going to take one thing out of this presentation, let it be this. The Nikkiso balsa liquefier was designed from the ground up to provide highly efficient and deep turndown. Our 30-ton per day liquefier can stably produce 9 tons per day. At this 30% turndown, we only consume 38% of our total power. At 50%, we're only consuming 56% of our turndown. If you look at the plot, you can see how all of our major subsystems turn down, neatly following the one-to-one curve. This is industry-leading performance and can really provide a boost to your project. Let's go into depth a little on how this really benefits your project. First, you have your direct power savings. Obviously, the lower your power in the liquefier, the better. But that's easy. Turning down deeper also means you can turn down your generation. Generation costs can easily outweigh your liquefier power, so a deeper liquefier turn down allows you to turn down your generation more deeply. So what does that mean? It means that if you're on a green renewable power grid that's unstable, say solar or wind power, and it's ramping up and down every day, this means you can stay producing liquid hydrogen for more hours in the day. Dawn, dusk, winter conditions, this liquefier can stay on. It also means that if you don't have sold out offtake, you can still purchase a plant and operate it in turndown while still giving yourself runway. Maybe if you have a 10 tons per day of offtake, buy a 15 ton per day liquefier. You can even buy a 30 ton per day liquefier, still operate at 10 tons per day. So it sounds like a really easy question. What's your design temperature for your plant? But choosing the wrong answer can be a catastrophe for you, because ultimately this is where all of your equipment gets sized, this is where it's optimized, and ultimately the liquefier is the most sensitive to ambient temperature. So choosing it right for this piece of equipment chooses it right for everything. If you have a cold day, colder than your design, you can see that your production will increase dramatically. If your generation system isn't sized to accommodate these cold days, you're going to have to turn down, and you're leaving potential production on the table. On a hot day, however, you're going to go down in production. And that means that now the liquefier is going to bottleneck. We've worked with customers to align these by looking at your local climate data. Let us help you run that analysis. So now we're moving to the downstream side of things. Once the liquefier feeds into a storage tank, there are 6 major sources of boil-off gas within a plant, as I've shown here for a representative system. Let's go through them all. First, we have tank heat leak. So whether you have a large storage sphere or bullet storage system, your tank heat leak is going to vary. Here, I've shown it with a 0.1% boil-off rate, a fairly traditional sphere. You can see that at this rate, it's a fairly minor contributor to the overall boil-off gas. But if you go with bullet storage, this number is going to dramatically increase and be a sizable effect on its own. Next, we have one of the largest contributors, which is flash gas. When you're using a hydrogen liquefaction system, you're going to have some amount of flash gas that's released as you bring your high pressure product down into your storage tank. Ultimately, this amount of flash gas decreases with higher tank operating pressure until it eventually is brought down to 0. On the flip side, there's also displacement losses. This is when you put a cubic meter of liquid hydrogen into your tank, you now need to get rid of a cubic meter of gas. As the tank pressure increases, that cubic meter of gas actually carries more volume. These two effects obviously negate each other and battle with each other. At higher pressures, displacement losses dominate. At lower pressures, flash gas dominates. Later, we'll get into how these two balance out and what the right operating pressure is for you. So let's hit the next 3. There's residual para-hydrogen reactions as the orthohydrogen turns into para-hydrogen. The industry is generally stabilized at around 95% conversion. Frankly, we think that's a good value, and we would recommend the same. The final 2 items center around trailer loading and your send-out system. Ultimately, as your customers' trailers go around distributing the hydrogen, they fill up with heat leak, which turns into pressure. This pressure ends up getting dumped out at your liquefier, and it becomes your problem to deal with, or your opportunity. Ultimately, because of the legacy of liquid hydrogen systems, most of these trailers end up being gravity fed, so they have to equalize with the tank pressure. That ends up releasing a large amount of boil-off into the system. I suggest that we take a page from the LNG book. If we install spray headers within these trailers and use pumps to actually force the liquid from the sphere into the trailers, we can take this to 0. So when you're considering your trailer solution, consider that. Finally, the trailer loading system and the hoses all have heat leak. It's a non-negligible amount, so don't forget it in your budget. So, as promised, let's talk a little bit about the pressure you're operating your tank at. As I said, there's a legacy of operating at relatively high, say 25 psig. And you can see why that was often the solution. It allows you an easy fill system and minimizes the amount of of total boil-off gas. But I suggest that we actually operate at a lower pressure. That ends up giving your customers colder product, which ends up improving the yield to the end user. Lower pressure hydrogen is the green solution. And these pumps have been successfully deployed in California and South Korea. Now, this doesn't look great. Why would I accept that much boil-off gas? It's because the balsa liquefier internally recovers that gas. And ultimately, the boil-off gas within the tank is actually lower at 5 psig than at 25 psig. Let's change how this industry thinks about tanks. So I talked a lot about boil-off gas and the sources of it, but now what do you do with that boil-off gas? Ultimately, your projects, if you have liquid hydrogen, you're going to unfortunately have boil-off gas. It's a fact. So you need a solution. Generation costs are simply too high for you to dispose of that hydrogen. It's perfectly good, cleaned up hydrogen. All you need to do is recover it and reliquefy it. Ultimately, that will improve the overall power efficiency of your plant. But you need to size your liquefier accordingly. Don't come in with a 30-ton per day generation system and a 30-ton per day liquefier and expect these to match. If you have 2 tons per day of boil-off gas, your liquefier is undersized. Maybe a 32-ton per day liquefier more meets your needs. Additionally, if you work with us and let us know, we can right size the equipment so that you don't even have additional boil-off gas management equipment. It can be integrated within the liquefaction system. So once again, work with us. We've worked with customers to make sure that your generation, your liquefier, and your send-out systems all play nicely together and are the right size. So with that, I think I'm just about out of time. I've got less than a minute, and so I will take any questions at our booth at D136. And don't forget to visit Nikkiso's other talk on the main summit stage in session 3 with our CEO, Peter Wagner. Thank you.